Imagine yourself aboard a spaceship traversing the cosmos at an unimaginable speed, almost reaching the maximum limit allowed by the laws of the universe, the speed of light. Now, close your eyes for a moment and think about time. How do you perceive it? The minutes, the hours, the days that drag on Earth. But what about out there in space, at this absurd speed? Does time behave the same way? When we move at speeds close to that of light, something extraordinary happens. Time, that old companion that has been with us since our first second of life, begins to behave differently. It speeds up, stretches, and compresses as if it's playing with our perception. Have you ever thought about what it would be like to live in a world where each second feels like an eternity or, on the contrary, passes in the blink of an eye? Imagine, for example, the light from the sun, which takes about 8 minutes to reach Earth. For us, it's an exact, unquestionable time. But what if you were aboard that spaceship, traveling at 90% of the speed of light? What would seem like a long journey of 8 minutes would turn into something completely different. For you, the star traveler, that same light beam would arrive in just 3.5 minutes. Incredible, isn't it? How is it possible that, for someone here on Earth, time follows its normal course, while for you, in the vastness of space, it speeds up so remarkably? It's as if the universe is challenging us to understand its rules, to dive deeper into this ocean of mysteries that surrounds us. Because, in the end, what is time? And how does it shape itself to the speeds we dare to reach? What do you think happens when we accelerate beyond what our eyes can perceive? Now, let's take this reflection even further. We've already started to see how time can appear different when we move at extreme speeds. But what really happens to time as we approach the speed of light? As your speed increases, something happens. Time, which has always been a constant in your life, begins to behave in an increasingly strange way. The faster you move, the more time seems to slow down. It's as if each second stretches out, elongating like a rubber band. So, what would happen to time then? Here, we arrive at one of the most fascinating concepts in physics. At the speed of light, time simply ceases to exist. For light, time does not pass. But how is this possible? How can something exist outside the flow of time? For a beam of light, the concept of before and after makes no sense. Imagine a photon, a particle of light, traveling through space. It leaves a distant star, crosses entire galaxies, and finally reaches us here on Earth. For us, trapped in our common perception of time, this journey might take billions of years. But for the photon, that time simply doesn't exist. For it, the journey is instantaneous, as if the entire universe were compressed into a single point of light. Now that we've started exploring the intriguing relationship between time and speed, it's time to dive into one of the most revolutionary ideas in modern physics, Albert Einstein's theory of special relativity. This theory reveals that time and space are not as fixed and absolute as we might imagine. Imagine you are on a train moving at an incredibly high speed, almost at the speed of light. Inside the train, everything seems normal to you. The clock on the wall still ticks regularly, and the distance between you and the next car appears the same as always. But what about someone watching from the outside, standing still at the station? How would that person perceive time and distance? Einstein tells us that, for this external observer, things would be very different. The time inside the train would appear to be passing more slowly, almost as if it were in slow motion. And the distance between you and the next car? It would seem shorter, as if space were compressed. All of this is because, according to special relativity, measurements of time and distance are relative. They depend on the speed at which the observer is moving relative to the object being observed. In other words, what you see and measure depends on where you are and how fast you are moving. This idea that time and space are flexible and malleable was a true revolution in physics. Before Einstein, it was believed that time was universal, that everyone in the universe shared the same clock. But Einstein showed that time is actually a personal experience, shaped by our speed through space. No matter how fast you move, light will always travel at the same speed. Whether you're standing still or running alongside a beam of light, the speed of light will always be the same for you, immutable and absolute. This challenges our intuition because, in our daily lives, we expect things to add up. If you run faster, you expect to reach something faster too. But with light, the rules are different. This constancy is the pillar that supports Einstein's entire theory. Now that we understand how speed can distort our perception of time, let's explore another equally fascinating concept: the impact of speed on the measurement of distances. This is one of the most surprising aspects of the theory of relativity, which challenges us to reconsider the very idea of space. Think about the distance between the Earth and the Sun. For us, comfortably stationary on our planet, this distance is approximately 150 million kilometers. According to relativity, as your speed increases, the distance between the Earth and the Sun begins to shrink. The very structure of space compresses. This means that, for an observer moving at an extremely high speed, the path that light takes to travel between these 2 points would appear shorter. It all comes down to the concept of length contraction, an effect predicted by relativity. When you travel at extreme speeds, the space in the direction of your movement begins to contract. It's as if the universe is adjusting to your motion, compressing the distances in front of you. This contraction only becomes significant at very high speeds, but it is a real and measurable phenomenon. We have now arrived at one of the most fundamental limits of the universe, one that humanity dreams of reaching: traveling at the speed of light. As much as we desire this, nature imposes an unyielding rule: nothing that has mass can reach this extreme speed. But why is that? And what are the implications of this limitation? Let's go back to that spaceship, accelerating faster and faster, trying to reach the speed of light. As you approach this speed, something remarkable begins to happen. The energy required to keep accelerating increases enormously. The faster you go, the harder it becomes to gain more speed. The reason for this is that, according to the theory of relativity, the mass of an object increases as it moves faster. This increase in mass demands more and more energy to accelerate, creating a cycle where the required energy becomes exponentially greater. At this point, the amount of energy becomes infinite. This means that, for an object with mass, no matter how small or large it is, it's impossible to reach this speed because there simply isn't enough energy in the universe to do so. Unless you subscribe to the channel to learn more about our universe. See you in the next video.